Rotation of the celestial body is an important phenomenon in physics. But we do not yet know the reason for this. Because the circular motion of one body is caused by the rotating gravitational field of another, it is said that without rotation there would be no orbiting. All systems like the solar system and the galaxy also rotate forever. Without knowing how the rotation came about and how it works, there is no longer any question of understanding what is happening in the sky. Because the speed, as explained, of a body m accelerated by acceleration, a, is limited to a maximum of v0, the kinetic energy of the body is of course also limited to a maximum. Then the question arises, where has the energy gone, which could actually have increased infinitely if the speed were not limited? If we consider the maximum speed v0 as the initial speed after the maximum speed of a body covered by the acceleration, a, then the speed would then be equal to the initial speed plus the product of acceleration and time. The speed of an accelerated body could have increased infinitely over time, that is, if it were not limited. Then the total kinetic energy would also result as follows. Although the speed of the body is limited, it is accelerated further, i.e. the driving force continues to work against the inertial resistance. As a result, the energy would have to be generated more and more. So the energy that would keep increasing has not disappeared, it has only been used up. Then we have to see how it is used up. Interestingly, this formula of total energy automatically consists of three parts. The first part, this is the kinetic energy of this body. Since the speed cannot increase any further, the kinetic energy remains unchanged. The second part, this is the work that the acceleration, a, has done after the maximum speed against the inertial resistance. Because the inertial resistance is equal to the driving force, this work results in the third part, this is energy that is still left after the driving force accelerates the body from zero speed to its maximum and has done the work against the inertial resistance so far and continues to do so. This energy is equal to that which could be generated at the beginning with the initial acceleration, a. That is, the initial force that did so much work was not weakened in the least afterwards. She could have continued to work with undiminished strength to accelerate the body from zero to maximum speed. Even then, there would still be a third energy left over afterwards. It seems unbelievable, but it is completely normal because this force would actually be able to generate infinite energy if the speed were not limited. It is strange that we cannot find an acceptor for this third energy who can use it up. But what happens to this force and where did this energy go that could have been created? In the video Unravel the Mysterious Behavior of the Gyroscope, Real Physics, number 7, we have already seen that a force will tilt its direction when it encounters resistance. This is exactly what has to happen here. If the straight line movement cannot be accelerated any further, another way out has to be sought so that this force can escape. When acceleration, a, accelerates a body and hits the body's inertial resistance, its direction is tilted. A weak point of degree of freedom of the accelerated body is the rotation around the x-axis. Then the driving force, the strength of which is the same everywhere for every point mass in the body, inevitably has to tip over in such a way that it drives the body to rotate around the x-axis. Because this overturning of the force did not cause any frictional resistance or the like, the strength of the force also remains undiminished after overturning. The direction of rotation of this rotation is also determined by the right-hand rule, with the extended thumb indicating the direction of acceleration and the curved fingers indicating the direction of rotation. Caution: the direction shown by the extended thumb is the direction of acceleration, not always the same as the direction of movement. For example, a rocket launched into the sky will rotate in different directions when it is still accelerating, and a returned space capsule when it enters the atmosphere and encounters air resistance. The phenomenon that the original straight line acceleration is converted into a rotary acceleration and the body rotates around the direction of travel is called grarotation. That is the basis of rotation in nature. The question about why the Sun, the planets, and the solar system rotate the way they are will be explained in detail later. Because part of the driving force in the direction of movement is always hindered by inertia and converted into rotational force, the body is rotated as long as it is accelerated. And it doesn't have to when its maximum speed is reached. So an accelerated body also rotates. Even if the body moves in a straight line, as long as it is accelerated. For example, a freely falling body can be viewed as a straight line movement. If it is accelerated by gravity, the radius of gyration is equal to the radius of the Earth. Because the radius of inertia is not the radius of the circle of motion, but the distance to the acting force. So even a freely falling body occupies inertial force, which opposes the gravitation of the Earth. This also converts part of the gravity into a rotational force. If the mysterious apple hadn't fallen on his head of all places, Isaac Newton would probably have noticed that the falling apple was also spinning. Then he could have saved us, humanity, a period of more than 300 years. Thank you very much for your attention. See you next time.